I titled this, and it was interesting to see in the program there was another presentation also had the word reflections in the title, and nothing to do with image reflections. It was all about looking back. And in my own case, I've been teaching with mathematics for 25 years. And even before that, I used SMP, and I actually gave a course in 1984, 5 and 6, using SMP for numerical and algebraic computing at my university. So it's actually even longer than that that I've been using it. I'm going to be talking, I think, here to an audience that agrees and understands many of these views that I have come to over the course of my teaching, but I am always reminded by many of my colleagues in physics that a lot of people don't use Mathematica, and so you still have to convince them why you should choose it as a tool. So some of my reflections are about that. And the first comment I would make, and even though this is a historical comment, by the way, can people at the back read that? Is that too small? It's okay, good. That the majority of courses around the world, I would say, are still using chalk and talk, very traditional ways of teaching, and in courses on simulation and modeling, computational physics courses, the vast majority of them still just stress the numerical techniques, on which I am no expert. But what I much prefer, and my own focus, is more on analytic or hybrid symbolic and numeric methods as my own research area, which is what I also try and communicate to students. So my views, upon reflecting about this, is that the standard approach, which is using some procedural language, and that may now be might be Java in some cases, and in the astronomy and astrophysics community, Python is by far the major language. But my view as an educator is if you're going to teach a language to a large number of students, and to give you an idea what I'm talking about large, our first year physics class has 1,000 students in it, so it's pretty large. They're not all physics majors, they're mostly engineers. Our second year class has about 90 students that are majoring in physics. Not all proceed through because they might be doing a second or third major, and our third year is about 70. And we use mathematical Wolfram language in all phases of that. I guess my view is that although learning procedural programming is, of course, very useful, my personal focus is more on exploration. And those that really want to get into the nitty-gritty and do lower level coding and need that lower level coding, that's great, but that's for another course. So another approach that people use in their teaching, I've called it a black box approach, is that you have a large range of specific applications that you develop, and I guess the demonstrations website is a very good example of, if you like, canned, semi-canned demonstrations, which of course you can unpack if you want and modify, which is very useful. And my own approach, for example, at the first year level, is to use a lot of the demonstrations to get across ideas rather than focusing on the code. One disadvantage, of course, if you want students to become computationally literate, that you don't necessarily learn a lot from the demonstrations. You might learn the fundamental concepts, which I think is the most important thing, but you don't learn programming or computation if you use this sort of more black box approach. And a third approach is what I have done increasingly over the last 25 years is an immersive approach, and I particularly have done this at the third year of our undergraduate program, where the entire course is given using Mathematica, Wolfram language, and the students have to do everything in that, including their final exam. So their final exam's in a lab, 3 hours, submit, and that's the way that it works. And it's very clear in that environment how effective that can be. What I also like is during the laboratory sessions that we run for this, as I'm walking around, and one of the ideas that I had fairly early on, and it was imposed on me due to computer limitations, was that we had a lab of 50 computers and we had 100 students. We could run 2 sessions, but I decided, particularly when they were starting on the System Mathematica, to pair them up for this particular structural limitation I had. But it turned out to be the best thing possible, because the 2 students working together achieved so much more, so much faster than one person nutting it out by themselves. And so I found that this accidental way of doing it was brilliant. And often I would just be walking around behind them and watching how they were attacking the materials that I'd presented them to work through. And that's where I saw whether what I was doing was succeeding or failing, not from the final solutions that they were submitting, but watching the process of them struggling with certain ideas, working through them, seeing what worked, what failed. And often what I thought was going to be the fundamental limitation was trivial to them, and what I thought was going to be really easy was they were struggling for half an hour trying to nut something out. So it was, for me, a great learning experience. And over the years, I kept modifying the materials to overcome many of those design errors in my work, which I think got better and better. And of course, the other thing was, as we all well know, we're up to version 11 of Mathematica. Each time a new version came out with new functionality, and I have to say I'm certainly not on top of all of the new functionality, and not only some fraction of it, but many of the things that we had done in a certain way can be done so much better. As I've said, I'm a physicist. I've been teaching it for a long time. One of the questions, we're using Mathematica, but what else is being used? And as I said, in physics, increasingly Project Jupyter and Python is being used, and it's a very good environment. It came up in John Fultz's talk, but I still see Mathematica as a better tool to teach. I won't even open the last one. I think you would know the answers. From a pedagogical principle, I would just raise something that often comes up in computer-based mathematics, computer-based learning, which is Bruno Buchberger pronounced something called the white box, black box principle. And I think this answers most of the criticisms that people have of the use of technology in education. And the basic of the principle stated here is that his view is that once you know how to do something by hand a few times and you understand the basic idea, then you can leave that to the computer from that point on. Now, my view is slightly different to that, but that's a useful starting point. Others have modified that. I'll let you read other views, and there's probably, I've only got the early history of that, but you can turn that around. You can try different ways of teaching, but I think the fundamental principle by Bruno answers many of the questions that people have about the use of Mathematica in teaching. Okay. When you're teaching, you can require students to learn Mathematica directly. This is good. You get to learn the software, but the downside is that you have to be on top of it. You've got to spend quite a bit of time teaching, and your teaching assistants also have to be on top of it. I often approach, and I guess my own approach to learning it, is to hack, to take somebody else's piece of code, modify it. And so usually I give students a template and they have to modify that to do something else. And that's their starting point. And I think they rather than a blank notebook, which is a bit scary, they start with some framework to work through. One of the disappointing things, possibly including on some of the aspects that I've done, is many courses using computer algebra, and also in particular Mathematica, the courses are still taking a traditional textbook and teaching it in a traditional way. And sometimes that's not at all bad. But in a system like Mathematica, there are so many different approaches you could take that perhaps you can actually revolutionize the teaching. That's a lot harder, more challenging, but I think potentially more productive. You can also write your own demonstrations. You can use pre-written ones, but my focus has been, certainly at the upper undergraduate level, is to get them using the system directly. May I just pause? I'm not sure. This schedule was for 30 minutes. Is that correct? Is that what people on the time? Okay, good. That's what I've got in the timing here. Good. Okay. Well, that's what I thought so too. And but they've given me a time and it's showing 14 minutes left.
We'll take the test.
Yeah. I mean, as I said, that's what it was in my program, and I'm a little puzzled by that. But anyway. Okay. So my goal is use and teach Mathematica. My course is based on problems, as all courses would be, and very few worked examples. Students work through them themselves. The advantages, I think, if you're doing the problems yourself, you get a deeper understanding of the concepts. You learn problem-solving techniques, and by immersing them in this, the students, I don't have that much of a focus on teaching the language, and I worked through Stephen's elementary introduction in 4 days when I was in Japan this year. I found it an excellent introduction. It's almost like, well, that I'll just give them that book and they can work through that. That's a good starting point, and if they've absorbed that framework, that's a really good starting point, which I think in many cases didn't have before. But as I said, in my own course, I have not focused on many lectures on Mathematica. I give an overview, one lecture, perhaps a little bit on programming, high-level programming in the language, and then we're straight into problem solving with the course. And this is a semester-long course where essentially weekly lectures of 1 hour and laboratory sessions of about 3 hours per week, and that's the framework that I've been working in. In my presentation, there's notes to, links to my courses on applied maths and computational physics. The applied maths was at a second-year undergraduate level, and the computational physics was at a second year and a third year. There's 2 courses there, so I've got links to those. I've sort of mentioned this already, but I have not implemented any automatic marking, and Stephen showed in his presentation some nice MOOC tools, and I think if I was going to redo things, that would be the way I would like to do it, where the student solutions are automatically interpreted and marked against a template, and I think that would be a more powerful way of redoing what I'd done. But I'm somebody who wasn't ambitious enough or had the time to try and develop a tool like that, and it's taken many years before I think the technology has matured to the point where that tool is now robust and straightforward. So I think that that would be an exciting thing to have, automate the marking, automate the feedback as much as possible. One obvious thing, though, compared to normal assignments, is that when the students submit a notebook to me, there's 2 things. One is I can rerun it. The second thing is I can annotate it and return it to them, and that's a real nice exchange way of doing things. So that's what I find useful. One of the other points, I mean, this is obvious to everybody here, I'm sure, but is that the students can show graphically, numerically, symbolically, visually, that their answer to a problem is feasible. And that's something that I strongly encourage, that when they get an answer, whether it's direct from Mathematica or a derived answer within Mathematica, that they don't just return the answer. They have to verify and justify that. And there are many ways to cross-check results within the system, and that's one of the true powers of it. I have mentioned, sorry? Yeah.
Just a quick question,
Yeah.
go back to
Yeah.
your notebook. Do you provide students with some sort of template notebook that they fill in, or?
I do. It's a very guided thing. If you download those, I won't do it now, but yes, it's very much a template-based thing where it's a step-by-step thing. And one of the issues, and particularly for the exam, if you're going to have a question that relies that the answer of one part feeds into the next part, I give them a whole bunch of checkpoints where even if they haven't got that out, they've got the checkpoint where they can start from this point. And so assuming your answer was this, and often once they see the checkpoint, they go back and they think, that's what I was doing wrong there, and they can go back and revise. And so many of them, it sort of hints to improve the solutions. But yes, it's a very much template-based thing. And as I said, the materials are there to download, and are welcome to have a look at them. You'll see very much it's a structured format that they work through.
One other question, is the the laboratories time limited? The students have to do it at a certain time?
The goal was, in that 3 hours, that they'd be submitting at the end of it, yes. But we had some flexibility about that, but our goal was, we're not trying to discourage outside learning, but I think the point is that you can spend too much time on things, and the point was there, some of the students were spending too much time. I mean, I thought it was great, they were fascinated, they were loving it. Other lecturers were starting to complain to me, saying, stop giving them so much time to work on this because it's impacting on the other courses that they should be doing. So, yeah, we ended up restricting the time. Yeah. As I said, I've also got links to the exam for the second year applied maths and I think I've actually given the links to my solutions to those exams, but there were lots of student solutions, and perhaps it would have been better to give a good student solution to those, to people to see. I think again, another obvious point, in the past, and this has got better with the future versions of Mathematica, the student experimentation is what I want, and that's what I actually saw in the computational labs as I was walking around, that students were trying out different approaches to solving it. And very often, well, a couple of things I found. Firstly, those students that had not done a procedural language before often embraced Mathematica much better. I suspect many people have had the same experience. And also, sometimes they would come up with an alternative way of doing it, and I go, that's actually far better than my solution. So sometimes and I would always acknowledge them, but I'd steal their solution and say, here's the solution from student Joe Bloggs from last year. It's a beautiful solution to this problem, and I found that really encouraging. I see Eric's here, so I better mention it. I tell them that there's a bunch of really useful tools, and you would all be aware of those, but in particularly physics and applied maths, obviously the function site, but also the DLMF, the Digital Library of Mathematical Functions, is really useful. And one of the embarrassing things I see there is academics do not, in the Digital Library of Mathematical Functions, they're still quoting Abramowitz and Stegun rather than the digital library, which is the updated version of this and has so many advantages using it. It's not perfect, and I would like to have seen a closer integration with Wolfram technologies there, and I know a bit of the story behind that. But anyway, it's definitely something I make use of, in addition, obviously, to the function site, which is a fantastic resource, the demonstrations and so on. So again, my point there is I'm somewhat lazy. I like to steal the best of these resources, and I'm often looking in the demonstration site. In fact, I have to say I was looking there this morning for something. Michael Trott did a reasonable, well, actually a very good conformal mapping app, but what I wanted was actually a simple one, and I looked through all of the ones there, and I can't actually find a simple one that I wanted to use later in today's demonstration, so I guess I'm going to have to write one, but that's a separate story. Okay. So just a few examples, and some of these are historical. They go back a long time, and some are much newer. This one was a problem that I set in, let me just read the data. There was a discovery of a variation in the timing of a particular pulsar. And the reason for this timing variation wasn't that the pulsar itself was changing its period, but what was happening is that the pulsar was orbited by a heavy planet, and so the pulsar was sometimes moving closer to Earth, sometimes moving away from Earth on our line of sight, and so the signal, there was a delay and a time variation in the signal. And this was the first proof that there were planets outside our solar system. There were bodies orbiting other suns, but well, in this case it was a pulsar. So what I got the students to do was import the data. I contacted, I think it's Alex Wolskan, who was one of the, at Penn State University, one of the discoverers. This is in 1994, I think I'm getting the students to do. So I got the data immediately from him, and I didn't do it back then because you couldn't, but later it was updated, importing directly from a URL. rather than sending a data file. And I try and encourage students, I mean, the cloud has replaced this to a large extent, but the point was, don't save files on your computer, save them on the internet, and so your notebook immediately becomes completely portable. Everybody else on the planet can use the same notebook, whereas if you have a file, you've got to distribute the files as well. So you import the data, and this is the structure of the data. Of course, we have other things we can do now, but so the second column is the decimal time in years, and I'm not sure what all the other columns, but one was the delay in milliseconds. I just mentioned, I know more dynamics here. Of course, you can use it as a data set now. By the way, semantic import just doesn't work on this, and I don't know why. I think it's a bug report to find out. But so this is a better way, a more modern way of doing it in Mathematica now. So again, these new tools come, and I have to keep changing what I was doing because there's better ways of doing it. And so another one, I did this differently previously, but now we use time series to analyze that data. And so we visualize the residuals there. We can plot time series now, and this is what you see for the millisecond variations in this pulsar. Now, for a physicist, the natural thing to think of is, I've got some timing variations, I'm looking for periodicity, Fourier, obvious. The problem is the sampling's not uniform. Now, you could resample, but there are issues in doing so, and the answer is, how do you fit functions to this? And so the approach to do this spectral analysis, which I teach the students, is essentially, and this was explained to me by my colleague, is if you're trying to observe the frequencies of some signal, use an idea of resonance. So if you've got a black box that's making some noise and you've got another speaker that's listening to it, you tune your speaker and you listen for the resonances when there's strong feedback or strong coupling between the systems. So the solution is to use linear least squares for one frequency, and once you do that, you can determine what's something called the spectral energy, which is this constant. So that's the physics there, which I get the students to do. So essentially what we can just do is do a fit to our time series for a sinusoidal variation. And again, if we plot that, this is what we see. And it is clear that there are two very strong periods there. There may be some others. And indeed, the conclusion is this pulsar is essentially being orbited by at least 2 planets, but possibly more. And that's the conclusion. And you can read off the periods about 23 days and 30-something days. The next part of the analysis, which I got the students to do, is compute the regression for this using a nonlinear model now. So our nonlinear model is a superposition of 2 sinusoids. And if you try and run this with this many parameters, without a good starting guess, at least for the frequencies, this just runs forever. But if you give it from that graph the maxima points, you immediately get a good fit, and your verification is quite beautiful. And this is the point. The students immediately could see that their answer made sense. And then you could go further and subtract this off and see whether there's still a periodic variation left. Is there a third planet? And Alex Wolfram did this and found a third planet orbiting as well. So that's the first example, an old one. But I think the students were excited because they were taking data that had been released that year and resulted in a Nature paper, and they were redoing the analysis already, and that was good. Next topic is complex functions. I wrote a little, it's not that robust, but just to do, I'll just hide here, it's a thing for doing a complex plot of a function. This isn't not a function within Mathematica, but why not do it? So I just generalized plot to do this, to show a plot. So because they're meeting in their third year, complex functions such as gamma, zeta, and they want a tool to visualize them. So these phase sort of diagrams are quite nice, and so they can see the poles and the structure of the gamma function. And the other one, which, apologies that I didn't switch that off, the next one here is a very famous one, the Riemann zeta function. And I explained to the students, who mostly are physics majors rather than maths majors, that there's $1 million prize if you can prove that the zeros of this function all lie, the non-trivial ones all lie along one line, the Riemann hypothesis. So I have a little bit to say about that as another example that I gave my students to work through later. But so the plotting is quite nice, well, it's very nice, and it gets them motivated. They can see their functions in their maths courses. Okay, I teach atomic and molecular physics as part of the courses there. The trivial example, which not completely trivial, but the example where you have things like, hide that there, there's better coloured diagrams of this, but I just had a table layout of the spherical harmonics, and you can do much more than I have done here, but SP and D orbitals, just as an example. But one of the papers I did was on visualization of atomic orbitals, and the point here is this is already just too complex, first to type by hand, but secondly to visualize, and so this is for a coherently excited F-state atom charge density for it. It's fairly complicated, yet you have all those parameters in there, and you can immediately visualize what's going on. And so the students are not, in one sense, they're doing some problems on these excited F-state things in the third year of their quantum mechanics, and so actually being able to get some feeling for them is really useful. So that was another sort of teaching example. I think Euler angles, and I see Dave Woodhoff's here, I haven't seen Dave for years. Dave educated me a bit about the Euler parameterization. We're talking about Euler angles, but we've got rotation matrices built in now, so this changed the way I did things quite early. They weren't there originally, and then even better, we've got transformation functions. So, and we've got also, I just mentioned, function composition shorthands. So for physicists, this is a nice way of putting things together, but none of that is powerful. But what is interesting is that when you visualize this, you can see very simply the effect of what the Euler angle parameterization is and changing it. And so the students immediately found that very useful. That's just another teaching example. Just as an aside, I don't teach chemistry, but one of the points is that when you have the free-form input, you can do things like balanced equations like this, which are, I think, highly non-trivial. And most of the chemists I've shown this type of example to go, well, I'd usually be doing ChemDraw or ChemPlot or whatever it is to do this. It's a much nicer way of doing it. And I could see, not my area, but it would be nice if these electronic chemistry lab notebooks, physics electronic lab notebooks, it was a framework in Mathematica to build them more easily. Okay. This is perhaps, I'll just show the demonstration. I had a Saudi Arabian student doing a PhD, Bahar Rafa, and we were working on quantum transport in nanowires. So he did my courses first, and this is part of his PhD thesis. His PhD thesis was very short, partly because instead of doing pages of diagrams, he would just it was submitted as a notebook. I don't know whether that's the first, having a PhD that was actually as a notebook, but it was examined in that fashion, and the examiners could see the validity of what he was doing by actually having not a PDF, you could get a PDF of it, a static version, but you had this interactive electronic document as a PhD thesis, which I thought was interesting. And his, this is one where in these quantum nanowires, you have a wire of long, thin wire, nanometer scale, and you can vary impurities and doping within this, and you're looking at electron transport through those. And this is, as I said, one of the things from the thesis where it's solving the quantum tunneling problem through that, and it was robust and simple to develop. So my point was he developed that after doing the courses that I'd done, so he absorbed the necessary tools to build something like this quite quickly. This is perhaps, physicists deal with Legendre equation a lot. It's one of the fundamental ones that we have to do. We can, of course, use dsolve to do this. I'm execute just to save time. And in traditional form, we get the Legendre functions, which is nice. But there's another way of solving this. This is it if you do it as an initial value problem. Firstly, this is nice where you show that as you change the parameter in that, where I'm changing n continuously, which is sometimes the case in physics that we need, how that behaves. That's a simple thing. But perhaps this is a little more interesting, is that if you wanted to solve that dE, one way is to iteratively do it via integration. So here I'm taking the differential equation here and essentially double integrating it, and I'm using a coercion series expansion there to do this, and the students could generate this and the solutions, including the parameters, up to any order. So I won't do that, but it's straightforward, and that I thought was quite a useful way of analysing the problem, because they were using series methods as well in the courses. Pretty much the last, I think it's the last example I want to show you. So last example was using the fast Fourier transform to do contour integrals, because in their by the third year level of their maths, they're doing complex function theory. They are relating it to their physics topics such as scattering, and they've got to understand and start doing contour integrals. And the relationship between, there are many ways of doing this, but the relationship between the FFT and certain types of contour integrals is that if you have a circular contour centered on the origin, if you are doing, let's say, a contour integral of this type, and I'll explain, well, I'll mention where this comes from. If you're doing a contour integral of this type, it reduces essentially to just a one-dimensional integral around that circle where theta is running between 0 and 2 pi, and I've done this for the unit contour. And the point is that these integrals here are essentially, linked there to Math World, these are just the Fourier coefficients, right? So the point is that if you sample the function around this circular contour uniformly, the FFT of that gives you the contour integral of, in fact, all of the moments of the, I'm here looking at the logarithmic derivative of this function, and the reason is if you have the power, if n is 1, you get the argument principle, you're essentially counting the number of roots within the contour, but this gives you all the moments of that as well. So here's an application to the zeta function, and as I said, that's one of the topics that they deal in the course. If you symmetrize the zeta function, that's done in their number theory course for them, you can just show that indeed once you've done that full simplify fails if I put that as an equation, but if I put it as a ratio, it works. I think that's correct, or it did the last time I tried it. So this is the fully symmetric version of the zeta function. So you've removed what they call the trivial roots of it. The point is this has a very simple product representation. But let me just end, this was something many of you will recall and know. Jerry Kuiper, one of the original Mathematica developers who unfortunately was killed in a bicycling accident, but he wrote a paper in 1992 which was using Mathematica, and basically under this complex transform, z goes to 1 over z, all of the roots, if they lie on the critical line, they're mapped to a unit circle centered on z equals 1 under the Riemann hypothesis. But if they're off the critical line, it still maps to circles, just not the unit circle. And here's an example of that where it doesn't look like a circle because the aspect ratio, but I needed to do that, otherwise it fills the whole screen. The black curve there is the unit circle centered on z equals 1. The green dots are the zeros of the Riemann zeta function, and this is the first one, the second one, the third one as you're moving up in the imaginary plane, and sort of as a limit point there of these. So the point is that if once you've done this reciprocal mapping, you can compute all of these spectral zeta sums, the sums of all of the roots, and to do this, essentially what you need are the moments of these contour integrals. And so they're dealing with these contour integrals. And the point is, actually, it seems like this would be a hard job to do, but actually computing the integrand, you essentially just define the, so I'm defining the 1 over z transform of the modified zeta function, taking the logarithmic derivative of it, multiplying by z squared. I won't explain why you do that, and evaluating it on the unit circle. And if you do that, you get a closed form, but involving these derivatives. And the key thing is that if you sample, so if I'm sampling, I'm using that function, I'm sampling it uniformly. I have to use this tiny offset. There's a singular point there. And if I do high precision arithmetic on this, what I end up getting are, it's a very, very fast process. I'm getting very accurate values of all of the moments, all of those zeta sums of the roots. And going back to Jerry Kuiper's paper, if you use a slightly modified function, if you can prove that all of these particular moments are positive, you've proved the Riemann hypothesis. So it's an alternative way of doing it. Anyway, the students work through that, and they also, just to relate it, firstly, we've done this using a contour integral, but instead you can just use a series expansion about the origin. Mathematica does this and gives you closed form expressions which get rather complicated as you go up to high levels. And if you check the values of the first few of those, they agree perfectly with the Fourier coefficient. So it's a very fast way to get all of the moments for this, because if you do it using the series method, it's arbitrary precision accurate, but much slower way of doing it. So that's an aside, but the basic idea here, I've applied it to the zeta function, with this basic idea, for many of these contour integrals, you can turn them into Fourier problems, which is a lot easier and a lot faster to do. Okay, so that's the topics that I was going to cover. Just as, what do I see from the students that have done these courses? And as I said in my university, in first year, they're doing an introductory physics course, and they're seeing Mathematica via demonstrations. In the second year, they're doing some labs, both in applied maths and introductory sort of computational physics. And in third year, they're doing much bigger projects. And 1 year, the assessable outcome of those projects was to produce a demonstration and have it submitted. So that was and accepted. And so that was actually quite exciting to them. Essentially, they were being published through that mechanism. So what do I see? I see that the students have improved model building and certainly improved problem solving capabilities. They learn a range of computational methods and different tools and techniques, some of them that are quite advanced, and they get to apply those early on. And I think by the end of it, certainly in the third year, they have a pretty solid understanding of the strengths and weaknesses and the capabilities of Mathematica in their research. My feedback, and this is, I've been analysing it for, as I said, about 20 years, the feedback. Yes, these response to questions, they become more competent. Yes, they've learned how to apply principles in new situations. Yes, the content's been challenging. Doing the assignments has been valuable. You know, all great things. But the other side of it, I would say, is that, this is particularly this point, it requires a lot of effort on my part to develop materials, work through them, get them in a robust state that they can deal with. And I would say for the students, and this goes going back to an earlier question, is that they end up spending a lot more time on it, both to learn the system and to work through the assignments. And some, if they're, say, an engineering major as well as a physics major, say it takes too much of that time. Others say it's time well spent. So I guess my attitude is I can't make everyone happy, so I'm going to do it the way I'd like to do it. You know, I really truly believe that there is no way of making everybody happy in what you do. So I think it's worthwhile. They learn a tool widely used by scientists. They certainly find the interactivity. Manipulate was a revolution there. All of my courses, once Manipulate came out, basically had to say, I'm going to rewrite all this. This is a much better way of doing so many of the things that were done before. Just on the demonstrations, I'll just, yeah, I've got it open here. This was an example what one of the students prepared. He's now a PhD student, where you can draw a random graph, and what he is doing something called PT symmetric quantum walks. That's for parity and time inversion. Most people think, in physics, still think that the Hamiltonian has to be Hermitian to get real eigenvalues. This isn't true, and it's been known. Carl Bender highlighted it back in the 1990s, but it's been known for a long time that's not what you need. PT, which is parity and time inversion, is enough to get real eigenvalues. And so for the question that this is Josh Isaac, one of my former students that's working on this, is can you, what's the question here? Can you implement PT symmetric Hamiltonians on a quantum computer when one's built? So how the algorithm, how would you make this thing work? And so he basically built this, this app, which I think is pretty neat. It's directed graphs, and you can see whether something is pseudo-Hermitian or whether it can actually be implemented in one of the computers. But the ability to draw these free form, that's probably a different node sort of thing there. I'll just clear that. I mean, he has a number of canned ones here, and you can say, well, what happens if I join up extra of the nodes and see, and that's no longer pseudo-Hermitian, and it's basically non-unitary, so it's not a valid quantum process, and you can't implement it in the quantum computer. So these are the sort of things that they're developing, and I quite like this as an example of the free-form, well, the easy drawing of the graphs that you were doing, and picking a 6-circle cycle graph and seeing whether it's a possible PC symmetric candidate. So once he developed this, in fact, for the research group, it became the tool all of them are using for trying out some of their ideas. He's actually got an extended version in which you can import and modify much, much larger graphs for actually working with, but this small-scale demonstration was just to show it. So the question I guess I often get asked is, what have your students learnt in the course, and have they benefited from it? And one of the answers is, well, those certainly that go on to higher studies, I know that they have, because I see them implementing really very interesting things using the system in a very nicely structured, elegant way. I guess I don't need to say any of these things, because these are all, well, one I will emphasize here, not this one first. I'll just mention we can have these user interfaces. Manipulate is absolutely essential for this. Curated data is useful. But the one question, the one topic I'll just highlight that I've used, in the third year exam, one of the processes I set for the exam is I'd give them a current research paper from JPhys or PhysRev, and the goal of their 3-hour exam is, I'd pick these carefully, but I'd say implement as much of that paper as you can in 3 hours, right, using Mathematica. And it works. I mean, I pick the papers so I know that they have enough of the understanding of the basics, and that's what's covered in the curriculum, but they can actually re-implement and understand a lot of what's done in these papers very quickly. So what I'm saying is you can ask research-based exam questions rather than canned trivial problems if you have an environment where you've taught them a good tool and you can ask them real questions. And so I'd say that's one of the features of my course that I'm proudest of, is the fact you can do things like this, but it's the tool, Mathematica, and Wolfram language that's enabled that. So that's the end of my talk, and I've left some time for questions.